What I'd like to go over today, or introduce today, is hypothesis testing. Both of the last topics on the syllabus, both of the last two topics in the semester, deal with hypothesis testing. One of the first of those is a situation in which we will be comparing a sample, and this is simply overview. It's a situation in which we'll be comparing a sample with a population. The second situation is one in which we will be comparing one sample with another sample. The second is the classic research paradigm. For example, one could compare the scholastic performance of males and females in that second situation by comparing the average score of a group of females on perhaps the GRE or GPA or SAT or whatever it may be, comparing that with the average performance of males on that same test or on that same measure. In the first situation, however, you're not comparing two groups with one another, but as I've indicated, comparing a sample with a population score. There's very little that's new, in a sense, about this chapter, Chapter 8. But I, at the same time, believe it to be the most difficult chapter in the text. And you should make special effort to come to grips with it by reading the text. Let me try and provide some order for you to the discussion in Chapter 8 and go at least part way through an example. If you recall, we looked at three situations when discussing interval estimation. We looked at a situation in which you were estimating mu, n was large, and sigma was known. We looked at a situation in which you were estimating mu when n was large and sigma was unknown. And we looked at a situation in which you were comparing proportional data, p subscript s with p subscript u, and n was large. We will be looking at those same three situations in the context of hypothesis testing, at least in the context of Chapter 8. And we will be looking at an additional situation, one in which you're comparing x bar with mu, but n is small and sigma is unknown. My point here is not simply to alert you to the new situation. It's more especially to indicate to you that in some way or another we've dealt with three of the four situations that we're going to look at in Chapter 8. There is an issue that we've not yet contemplated that arises in Chapter 8, and you needn't write this down at the moment because we'll go through it. And that is the issue of whether a test should be one or two-tailed. Having said those things, let me overview the logic. The question is, can I repeat the last thing I said?
Whether a test
the issue that we've not discussed, did not discuss in the context of Chapter 7 or anywhere else, was the issue of whether a test should be one or two-tailed. And what that means and how to decide that issue is something we will cover not only this morning, but repeatedly through the context of this discussion, because it's a decision in every problem, in every circumstance. Let me, having said those few things, sort of overview the logic of hypothesis testing. We return to the sampling distribution of sample means. We could also be talking about a sampling distribution of sample proportions, but we return to the sampling distribution of sample means. We know that this sampling distribution has a mean equal to mu, and it has a standard deviation equal to sigma over the square root of n. I presume everybody would agree with that. We encountered it repeatedly in the context of interval estimation, and it derives from central limit theorem. We will be comparing some sample score with mu. That is, we have to somehow find a way of fitting the sample score somewhere in this distribution. What we're going to do is, following up on the idea of beyond reasonable doubt, we're going to set alpha equal to 0.05 or 0.01. That is absolutely equivalent with 95% confidence intervals or 99% confidence intervals. And we're going to identify regions at one or both tails of this distribution. I think this is intuitively obvious. If this is the average, would you agree that the further you depart from the average, either in a positive direction or in a negative direction, the more statistically deviant you become? If you score 1770 on your SAT, you are statistically deviant because you're way up at the positive end. If you score 420 on your SAT, you are statistically deviant because you're way down at the negative end. If you score approximately 1,000 on the SAT, you're somewhere very close to the average. In hypothesis testing, what you're looking for is the statistically deviant. Down at this end, this negative end, I've characterized it jokingly before as the Quasimodos and the elephant men of this world. Uglier than the average. At the top end, we have Brad Pitt, Denzel Washington, for the older, like my wife, Sean Connery. Well, some guys have all the luck. Isn't that what Rod Stewart said? The physically fortunate of this world. Most people are not of that kind. Most people do not depart significantly from the average. So the logic is this. When we take our single sample score and place it in this distribution, if it falls in one or other of these shaded areas, we will reject the null hypothesis. We will reject the null hypothesis. The null hypothesis, you recall, is a statement that says that two scores do not differ significantly from one another. If, however, that single sample score, when placed in this sampling distribution, is somewhere in this clear area, we will fail to reject the null hypothesis. We will fail to reject the null hypothesis because we will conclude there is no significant difference between that score and the mean of this distribution. And that, in overview, is hypothesis testing, at least in the context of Chapter 8. Are there any questions to this point? You should not be worried about detail. I will tell you that, because we're going to go through this repeatedly. You will read through chapter 8 and you will discover that you will discover, as I've indicated, 4 situations. And it's possible that you will look at those 4 situations as 4 unique situations, 4 very different situations, because they look very different. The process of hypothesis testing, however, does not change. It does not change regardless of the situation in which you find yourself. It is comprised of 3 steps. Step 1 is to define the critical value. Define the critical value of the test statistic. And whenever n is large, as it will be in 3 of the 4 situations, whenever n is large, that test statistic is z. In the other situation in which n is small, that test statistic is t. But we will come to that. In order to define the critical value of the test statistic, you need to decide two issues. The first of these is the level of alpha. The researcher sets the level of alpha, so we can determine the level of alpha very straightforwardly, 0.05 or 0.01. The second thing is to decide whether the test is one or two-tailed. Let's take a look at an example. On the first page of chapter 8, page 181 of the text. Page 181 of the text. But as you look to the bottom of page 181, right at the bottom, at problem 2, are the GPAs of college athletes different from the GPAs of the general student body? To investigate the academic records of a random sample of student athletes from a large state university are compared with the overall GPA of all students. So we have X bar, and X bar applies, would you agree, to student athletes. And then we have mu, which applies to all students. Let's think in terms of the research hypothesis H1. What is the relationship that is posited between X bar and mu? And you have 3 choices here. Choice 1 is that they are not equal, that they are different. Choice 2 is that X bar will be greater than mu, and choice 3 is that X bar will be less than mu. You cannot, if you recall when we discussed the null hypothesis, the researcher cannot hypothesize that the 2 scores will be equal. That's the presumption that is being tested. That's the null hypothesis. So, to return to my question, in this problem, what is the hypothesized relationship between X bar and mu? Yes.
I'm going to take a guess because I think I understand how this is going, but is it X bar is less than mu?
One person says that the hypothesized relationship is that X bar is less than mu. The answer is not on the screen, and as my math teacher used to say, the answer is not in my face. The answer is in the text. In fact, it's in the first sentence of the problem. Are the GPAs of college athletes different from the GPAs of the general student body? We now have somebody squeaking, not equal. You're opting for choice one.
But I have a question. Aren't they all not equal? Because greater than and less than is not equal also.
No. Yes and no. Yes and no. That point becomes absolutely critical in a moment. But does this first sentence read, are the GPAs of college athletes lower than the GPAs of the students? It does not. Option 3 is gone. Obviously not the week to go to Vegas. Does it read, are the GPAs of college athletes higher than the GPAs of the student body? No. Option 2, gone. It says, are they different from? Surely then the research hypothesis is that they are different from. So that the hypothesized relationship, the research hypothesis, is that X bar will differ from mu. This is all part of the process to decide whether the test is one or two-tailed. Would you agree, I'm sure you would, because you just said this, would you agree that this condition can be satisfied by either of two outcomes? It can be satisfied if X bar is less than mu, and it can be satisfied if X bar is greater than mu. Would you agree? So you have to test, when testing this hypothesis of simple difference, you have to test for both negative difference and for positive difference. Yes? That is, you have to test both the positive tail of the distribution and the negative tail. You must conduct a two-tailed test because you have to test for both negative and positive difference. Which means that if alpha is 0.05, that you deploy half of that 0.025 at the positive end of this distribution and half of it at the top end of the distribution. Having done those two things, we can now decide the critical value of the test statistic. Let me ask you this. If alpha is 0.05, and if we think in terms of a standardized sampling distribution of sample means, and all that means is a sampling distribution in which the distance across the x-axis is measured in standard deviations. And now if we think we've got 2.5%, that is half of alpha up here, and 2.5%, 0.025 of alpha down here, how many standard deviations do we have to go out each way to isolate 95% of all of the scores? Pardon? Come on, sports fans. This is a giveaway. This is a giveaway. Let me ask you this. What is the value of Z if you are generating a confidence interval at 95% level of confidence? Why is it 1.96? Because if you go out 1.96 standard deviations in each direction,